When it comes to electrical energy, there is a lot of confusion people nowadays make, especially when it comes to alternative current or AC. Well, if you don't want to be one of those guys who spread misleading information, keep watching this video. Unlike DC, in AC current there are 4 types of power. Active power, measured in watts, reactive power, measured in volt-amperes reactive, apparent power, measured in volt-amperes, and deformant power, also measured in watts. If we multiply power with a unit of time, we get energy. Active power is equivalent with the same amount of DC power that would generate the same amount of heat in a resistive load. In this example of DC circuit, the input power is electrical power and is defined as the product between voltage and current. The output power is the heat generated by the resistor and is defined as resistance times current squared. Both input and output powers are always equal and are measured in watts. The same rule applies with an AC source. However, the formula is a little bit different. This can be visually interpreted with power vectors. Active power is the only type of power that can be converted into mechanical work, heat, light, and so on. The formula for active power is voltage times current times cosinus of alpha, where alpha is the phase angle between voltage and current. On a pure resistive load, cosinus of alpha equals 1, therefore is neglected. And so we get to the same formula as in the previous DC circuit. You should know that as a house owner you only get charged for active energy consumption. The next one is reactive power, which is 90 degrees out of phase and it does not create any mechanical work nor can be converted in anything else. The formula is voltage times current times sinus of the same alpha as before. Only big companies are charged for the consumption of reactive energy, and I'll explain why later in the video. Completing the right triangle is the apparent power and it obeys the Pythagorean theorem. The formula for apparent power is simply voltage times current, but this one should not be confused with DC power. This drawing is the base concept of AC and it is called the triangle of powers. A quick reminder upon angular frequency. Assuming we are continuously drawing the circle anti-clockwise. With black color we have decimal degrees and with blue are radian degrees. So from 0 to pi is half a circle or 180 degrees, then another half of circle and we have 2 pi and so on. AC current is a repetitive sinusoidal function. So here we are at the phase angle. In an AC circuit with a resistive load, both voltage and current are in phase, so the angle between them is 0, which means only active power is flowing through this circuit. In an inductive circuit, however, the current is lagging behind voltage with 90 degrees or half of pi. If you remember the previous formulas, cosinus of 90 degrees equals 0 and sinus of 90 degrees is 1. So in this example, only reactive power is flowing. In a capacitive circuit, the situation is reversed. Voltage is lagging behind current with half of pi. The phase angle is still 90 degrees, so only reactive power is flowing in this example as well. But what's with all this active-reactive nonsense? Why can't we just keep it simple and have one single power as in DC? Well, keep watching because here comes the fun part. Let's make a simulation and try to solve this mystery. In the first example, I'm using a circuit with a resistive load. I'm choosing a sinusoidal AC power supply with a peak amplitude of 10 volts and a frequency of 50 Hz. And for the sake of simplicity, I'm choosing the current amplitude to be half of the voltage amplitude. So in order to get 5 amps of current flowing, Ohm's law says I need a 2 ohm resistor. In this simulation I will plot the waveforms of voltage across the resistor, current through the circuit and apparent power. As it was expected, both voltage and current are in phase. If we look on the power graph below, we notice that the flow of active power is always positive even when current and voltage goes below 0. This is because negative voltage times negative current equals positive power. Now let's delete this resistor and replace it with an inductor. Again, I choose the value that gives the current amplitude equals to half of the amplitude of voltage. In this simulation, we can clearly see current lagging behind voltage with a 90-degree phase shift, which is 5 milliseconds at a 50 Hz frequency. Also, the power waveform is no longer positive and it alternates with equal amount both above and below zero line, which means the reactive power does not flow in one direction like active power does. It simply comes and goes 50 times a second. Think of it like a car suspension. It continuously compressing and expanding during movement, but it always has the same length when it's at rest. Finally, let's try the same simulation with a capacitor and plot the values to see if anything has changed. As you can see, in this case, the voltage is lagging behind current with 90 degrees, which means the power should look the same as in the previous example with the inductor. Or is it? If we put them side by side, we notice there is a 180-degree phase shift between reactive power flowing through the coil and reactive power flowing through capacitor. Therefore, the two powers are opposing each other. As a rule of thumb, induction circuits like coils, induction motors, transformers, and so on need reactive power in order to magnetize its magnetic core. Therefore, we say that inductive loads consumes reactive energy from the grid. On the other hand, capacitors generate reactive power and are generally used for power factor correction, but more on that on another video. In essence, active, reactive and apparent power forms what is called the triangle of powers. But what is the formant power? You don't hear about it so often, right? Well, in previous examples I have used ideal circuits. In reality, neither voltage nor current are perfectly sinusoidal. Every load that is not an incandescent light bulb or resistive heater induces harmonics in the power grid. Harmonics are sinusoidal currents with higher frequency and lower amplitude than the 50 Hz fundamental frequency. Let's simulate that by adding another voltage source with a lower amplitude and 3 times the fundamental frequency. Now both the voltage and current are distorted. The third harmonic is added over the fundamental. As a result, the power flow is also composed from active power generated by the fundamental and the formant power generated by the third harmonic. In the FFT spectrum we can distinctly see the 50 Hz fundamental and also the third harmonic with a frequency of 150 Hz. Let's add another harmonic and see if we can form a pattern to conclude this video. So let's start by adding another power source with lower amplitude and a frequency of 250 Hz. This is called the fifth harmonic. Now the waveforms looks even more distorted and the FFT spectrum is composed of the first order harmonic or fundamental and also the third and fifth order harmonics. But do you notice any tendency here? It looks like if you continue to add harmonics, the waveform is starting to look more like a square wave. In fact, a square wave is composed of an infinity of harmonics. As we can see in the FFT spectrum, the program cannot simulate all of them, but there is also no point in doing that, because only the first couple of harmonics have a high enough amplitude to affect the energy quality. Now we can draw the two most important conclusions. The flow of reactive power is bad for power companies as it generates an additional current flow which overloads the power lines. Therefore, power companies must oversize their electric generators and upgrade the infrastructure to work with apparent power instead of active power. This increases the cost and generates financial losses. The flow of deformant power is bad for consumer because it lowers the quality of energy. Imagine an induction motor plugged in such a low quality grid. The 50 Hz harmonic will drive the motor at a certain speed. At the same time, the 150 Hz harmonic will try to drive the motor with 3 times more speed and so on. Meanwhile, all this deformant energy will convert into heat and will lower the efficiency and lifespan of the motor. The biggest sources of pollution with harmonics are switch mode power supplies, like those contained in computers, fluorescent and LED light bulbs, arc welders, and so on. If you like this kind of content, share it with others and also subscribe to this channel for more videos to come. Thanks for watching and see you next time. Bye!